Thanks for tuning in. We are going to give a talk about our computational textbook that we wrote for teaching data science with Julia. My name is Travis. I'm a software engineer in the ECE department at the University of Michigan.
Okay, and my name is Raj. I'm a professor in ECE as well. I'll tell you a little bit about this textbook and how we use it to teach a large class in computational machine learning and data science. But before we get there, I want to tell you a little bit about the author's perspective that has to do with why we created this new type of textbook. So here's the way we thought about it. There are a lot of things about printed books and web pages that we do like. What's nice about books, especially a well-written book, is that a book makes it feel like it's a conversation between the author and the reader, across space and time in some way. And it's nice to read a math book which has beautiful fonts and typesetting, and it's a joy to read a well-written book and often to reread it as well. What's great about computational notebooks, for example, like Jupyter or Mathematica, is the ability to show the algorithm working with figures that are generated when the algorithm is running live. It's nice in these computational notebooks to be able to mix math and exposition and have inline code. This is something that printed books and web pages can't do. The reproducibility component in computational notebooks gets tricky sometimes, but it keeps getting better. What's not nice about computational notebooks is often it's written in a format where you can do run all. And from a textbook and instructor's point of view, there is this syndrome, which is the students press run all and learn very little. So the starting point for why we wanted to create a new type of textbook was that we wanted more than what these other formats are able to deliver. So our greedy wish list, kind of like the greedy wish list that the Julia founders had when they created Julia, except ours is a wish list for a computational textbook, is that we want the best of what printed books, web pages, and blogs do, which is this static notion of a deep conversation. We want what is the best about computational notebooks, which is the mixing math with code and exposition and being able to run it live. But we want more, and the more has to do with we want a dynamic experiential conversation with the learner where the material is revealed as the student progresses through the material and is ready for that kind of conversation. Particularly what we have in mind, the idea in terms of this more has to do with connecting the learner to this idea that when the different pieces of algorithms come together and they work, there is this great aha moment where the student experiences this connection with maybe the first person who linked the math and code to do something almost magical, so to speak. Other aspects of the books that we'd love to incorporate, which go beyond books and notebooks, are the ability to personalize the book based on the learner's own observation, the ability to reveal, often the most fun part of learning machine learning or computational sciences, the various subtleties, particularly the strengths and weaknesses of algorithm via experimentation, in a way that you can't really do in a printed book, because in a printed book, you're worried about how many pages you have to write or print out and how to format these things. The part for me, as an instructor who likes some of these subtleties, but also teaches a large class, is I've always wanted to write a book where I could hide within the book certain hidden sections. You can think of it as Easter eggs, like in a video game, where learners who want to learn more can sort of unlock these sections, but other people who don't really want to dive in deep don't know that they're there, so we're not really discouraging them. And the design focus in terms of integrating these portions is how do we encourage and engage the reader / learner in what's to be done instead of what's left to be done. So the answer in terms of how we did this in the computational textbook format has to do with this concept of a codex, and Travis will say more about what a codex is and how we create it, author it, publish it, and distribute it.
Yeah, thanks, Raj. I'm a software engineer, so I get to talk about all of the software that we actually built to make all our dreams reality. So like Raj mentioned, the thing we came up with is a codex. And so a codex, self-contained, interactive, and computational are kind of the three key tenets. It's self-contained in that we really try to make each codex stand on its own. You can almost present them in any order, and we like to really present material just in time when the students need it, so that they're not burdened by long exposition and they finally get to the fun part. It's interactive in a way that a physical textbook and even a Jupyter notebook really can't be. And that gets back to this way that we progressively reveal the content when students are ready for it. And finally, of course, it's computational. Computation is really at the heart of what we're doing here. We want students to explore their data computationally and just learn. So what is Minerva? Minerva is the logo you saw at the beginning, and Minerva it's the platform that we really have used, we've really developed to make all of this possible. So it's where we author, distribute, and where students get to actually run these codices.
So here we have a pretty simple demo codex. One of the first things you'll probably notice is that there's not a lot here right now. The reason for that, like we mentioned earlier, is that these codices are progressively revealing and are designed to present material to students when they're ready for it. So the way that codices work is that there are multiple types of questions that students might have to answer to be able to move on to the next section. So the very first type of exercise, and probably the most common one, are these multiple choice quizzes. They're a great way to provide instant feedback for a student to check their understanding. And you can see once we select all the right answers and click submit, we move on to the next section. The second type of exercise are auto-graded exercises. These, we typically ask students to implement some kind of algorithm like gradient descent or completing a matrix using the SVD. The way it works is by comparing the student solution to an instructor solution. So here we can see what happens if, for example, I submit an answer that's just plainly wrong. You see it says we didn't get it, and if we look, it tells us that we didn't pass the test cases. So we can try again and maybe do it right this time. And now you can see we're on to the next section. So here we have validation exercises. These we typically use to make sure that a student meets some kind of numerical threshold. Typically, it'll be something like the student is asked to design a neural network in a very open-ended way, and the only requirement is that they achieve some minimum test accuracy. So, for example, it asks us to define a positive number. We can say no, and we are not allowed to pass. And then once we have trained our neural network to present the correct positive number, you can see we can move on. Finally, we use free response exercises to allow a student to remark on what they're observing. Typically, they might be asked to describe a data set qualitatively or figure out why an algorithm is failing on a certain set of examples. We really like to use the open source interact.jl project to allow students to easily and interactively visualize the data. This toy example asks us to pick our favorite trigonometric function, and of course we pick sine because we're not monsters. These different types of exercises are really only the jumping off point when you're writing a codex. The real magic comes when you, as an instructor, get to string these different types of exercises together to create a sort of computational narrative, guiding students through the process and showing them where they're likely to get stuck and how to get unstuck.
So when you really think of doing all this computational stuff, the first thing that comes to mind is, of course, Jupyter. And originally, we used Jupyter. We used so-called vanilla Jupyter to teach several courses at Michigan. And over time, we have realized we ran up against that run all, learn little syndrome very early on. And so we tried to say, can we make these Jupyter notebooks better in this way? And the answer was, yeah, we could, up to a point, really. So Jupyter it really can only be modified so much. There is a certain set of hooks where they let you, the Jupyter developers, let you insert your own functionality so that you can maybe render a different data type or add some functionality to the cell toolbar. But once you start to go beyond what those hooks are designed for, it gets really, really difficult. And the fundamental issue is that Jupyter is a tool for writing these computational notebooks. Typically, they're things that you then might want to go share with other data scientists so that you can verify your results. And that's just not what we're doing here. So we decided to really build Minerva as an independent platform. So the first thing we did, of course, was we said Minerva is going to be this interface that's designed to promote student learning. We really want students to focus on what actually matters, which is the code, the content, the plots and figures, all of that. We got rid of a lot of just extraneous stuff that is either confusing or not relevant in this context. And it was really designed from the ground up to avoid that run all syndrome. Additionally, it lets us do cool things like adding in teaching staff in grader modes for, let's say, teaching assistants who are walking around a lecture hall or graders who are verifying homeworks through Gradescope. And finally, Minerva is really just its own platform. Owning the whole stack, so to speak, really lets us just do things that are just impossible with Jupyter and trying to glue together lots of disparate open source tools and projects. So Minerva is this full-on platform for authoring, publishing, and distributing codices. There are really kind of three core components of Minerva, which are the infrastructure, and that ranges from kind of the more boring plumbing side, from actually having servers to run things on and signing users up and adding them to the correct courses so they can access the content, all the way up to the more complicated things like spinning up Julia processes on the cloud so that students have a place to run their code and view their plots and figures. There's the distribution aspect, which is how essentially codices go from an instructor to students. So right now, typically, codices can be released at specific times or released now. So you might want to release a codex at the end of your designated lecture period and let students work on it. And finally, authoring is something that we're really working on. We believe that codices are a really great way to present content like this, computational textbooks, computational lab supplements, whatever. And so we're working on an authoring platform, but it's not quite there yet. So stay tuned. And finally, Raj is going to talk about all of the instructors' perspective.
Okay, thanks, Travis. So the idea I hope you've gotten is that when you write a computational textbook in this way, there are many ways one can try to use it. And in the class that I teach at the University of Michigan, the course is called Computational Learning and Data Science. And I've written a textbook in this form, which has multiple codices that take on the role of these chapters. They showcase various machine learning algorithms of the kind you would expect in a normal class. So for example, in this course, it's a Julia-centric focus, so there are codices on Intro to Julia, a codex set on the foundations of computational linear algebra, least squares, different ways of fitting system equations, and other machine learning algorithms, some of which are listed here. But the important aspect in the way that we've been emphasizing is not the content on its own, it's how the content is written and how it's delivered in terms of these multiple ways in which we link the concept, math, and code throughout the codex. So when students encounter this in the course, or a learner who purchases the textbook and tries to read this chapter, unlike a regular textbook where they read everything, here you can't read everything. You start with only the first portion of the codex that's displayed to you up to the first multiple choice question, typically. You answer that, and then the next portion is revealed, and then it keeps going on. So students really learn by doing. This is not a book for reading as much as it's a book which is more step-by-step guide for doing. And what makes it fun from an authoring point of view is that every codex, partly having to do with the very many cool applications of machine learning has some nice applications where these different components of the code that are built up throughout the codex come together, and the student gets to see all of these things work in the way that it's expected to, and we break it so that you can see how they can maybe fix it or computationally reason about it. So some of the many applications that students work with via the codices in this textbook include in-painting, writing on your screen, for example, to recognize your own handwriting with code that you built from scratch, as opposed to, for example, the Jupyter way, where you download somebody else's code, you run it on an MNIST data set, and then you just hope and believe that it works on yours, but never actually run it on your own handwriting, so to speak. Okay, so if you want to try this out, there's a link for it on the Minerva site, and that's the textbook that we use in the class. So a question that often you might come up with is, okay, what happens if you use this in a large class? Does this accomplish some of the authoring goals that I laid out in the beginning in terms of having deeper conversations? And how do students react with it? So I'll start from the instructor point of view. The class that I've taught, the way that we teach it is we have the first hour and a half of the 3-hour slot being a regular lecture. So you can kind of see on the left picture, I'm sort of lecturing with a usual set of slides. After the first hour and a half, where I've given them just enough information to do what's in the codex, typically like the first half of the codex material is almost repeated in some lecture kind of way. Then the students bring out their laptops, the codex is released, and then they work on the content, which means actually computing and linking the math, which is omnipresent in machine learning, to code, and seeing the various kinds of ways in which the code works, doesn't work, or reasoning about it. So an important aspect of what happens when this codex is deployed in this way in teaching and instruction is that students work in pairs together or in groups. We encourage that. Some folks, of course, work on their own, but they find that working with each other is a great way to deepen their understanding. But also, frankly, one of the key skills in computational sciences is being able to debug code when it's not working. Frankly, this is what we do most of the time. And students benefit, and they realize that they're benefiting from working with people and seeing how their code is not working in these auto-graded programming assignments. From an instructor point of view, one of the things that's important, this is highlighted in the box at the lower left, is that you can have much more deeper conversations with students on the details of the algorithms when they're stuck or when they encounter it, as opposed to sort of in the sage on a stage mode saying everything from the beginning. It eliminates, from the instructor point of view, the stress in grading, because the platform is taking care of all of the grading, and all of the questions and quizzes have been tested on over 1,000 students. So you can have that confidence and peace of mind. Students are working on the code, but they're also operating at a much higher level. The philosophy for ML really is that it doesn't matter what you say on the board. If you can't program it, it doesn't matter. And this way of teaching and this way of sort of adopting the textbook brings those aspects into focus in a way that makes it fun to teach a large class, because you as an instructor spend more time interacting with students on things when they have questions rather than trying to preempt questions from the beginning. Here are a couple of the comments that students have had when they worked with this. You know, we've tried it so far at Michigan on over maybe 600 students, at MIT at over 100 students, and in various private camps with over 100 to 150 different scientists and engineers. And folks like this about the platform, and the conceptual questions and just-in-time assessment has proven to be a hit. There are a couple of things that become important, maybe even more important in this COVID era, which is, does this way of teaching with this kind of textbook using Minerva scale? So here are some numbers of what we did. We had about 265 students last fall in 2019. And for the upcoming fall, we have over 300 students. In principle, the platform can support thousands, so that's not an issue. And really what allows it to scale are two aspects. One is, of course, the Google Cloud auto-scaling, which is built in to the way the Minerva platform has been architected, and that's by design. The next two aspects have to do with the portion, which is the human-related scaling aspect, which is, what do you as an instructor have to worry or not worry about? And the most important thing as an instructor is that when you have 300 students, you don't have to worry about grading, because the platform is really doing the program checking. So you don't really have to worry, am I going to get 300 homework problems that somehow you have to grade or your graders have to struggle to grade? And you might imagine programming assignments are particularly notorious to grade, and the textbook and the platform has a lot of those hooks built in. So you can worry, or rather enjoy addressing students' questions rather than worrying about is the homework difficult enough or gradable enough. The last aspect about what allows it to scale is that when people get stuck and everyone gets stuck, they don't get stuck at the same point and they don't get stuck at the same time. So what that means is in a class of 300, you have some students who kind of race through the math and get stuck at the programming. There's some folks who kind of get stuck in the programming and don't know and are confident with the math. And then some folks who get stuck at various points in between. So when we've taught a class with 300 students, we're able to support it with just 4 lab instructors or 5 lab instructors at a time, because it's not like all 300 are getting stuck at the same time, right? And the combination of these 3 factors allows, from a platform point of view, it to scale, and also from an in-person or an online Piazza-aided way to scale as well. There's a couple of questions related to what we'd love is if you were interested in trying this for your course, you might wonder, how do you adopt this? The way I do it in my class is to have this regular 1.5-hour lecture followed by the 1.5-hour lab component, so to speak, where they work with the codices. What you could do is you can take your favorite textbook and notes. My perspective on this is there's really many, many different excellent ways to talk about machine learning algorithms. Different ways of talking about it all complement each other. So it's not an either or, it's more how do we give students exposure to many different ways of theoretically talking about it, but very concrete experience with programming it. So you might supplement your favorite textbook or your own notes with the Minerva textbook as homework or in-class lab. And the way I've written at least the textbook, my hope is that it amplifies your voice and allows you to have a just as needed deeper conversation with students when they're stuck, instead of worrying about the details of, is it going to be graded? Does the program work? If they download Julia code, is it the same version as what you had when you created your assignments? All of that you don't have to worry about, and you can focus on the concept instead of grading, which is what Minerva does best. Before we pause a bit to allow you to demo the platform, because really, as much as we've talked about the students, the most important thing is whether you believe some of these aspects in terms of the experience when you experience it yourself. So there are a couple of people we want to thank. I'll start off with a few in the beginning, and then Travis will also add in his shout out. So Dave Sanders from the Julia community started some of this off by giving me a hint, if you would, by a post on the Jupyter forum for how we might do these sequentially revealing notebooks. There are other folks at Michigan, MIT, particularly Giannis, Simon, Alan Edelman, Brian Moore, and Adrian, who've helped in different versions of the of what Minerva has become now. And Travis will add a bit more.
Yeah, shout out to Shashi for dealing with me and everything relating to WebIO. And there's no way that all this would have been possible without just how incredible the Julia community has been, and also all of the amazing open source stuff that we get to build on that's in the Jupyter project.
Okay, so there's a couple of things before we give you the plug for the demo at least. One is, maybe you're wondering if you'd like to author your own computational textbook this way. The short answer is the authoring tools will be available in 2021. They're not ready yet. There is a version of the authoring tools, obviously, that I've used to author this book, but it's not quite ready for someone else but me. If you're interested in writing a computational textbook in this way, after you've demoed what such a textbook could look like and maybe believe that author vision that I started off with, check out minerva.io, and there's a form where you can indicate interest, and then we'll get back to you. And finally, we wanted to leave some time, at least in this Julia presentation, where you could try this yourself and ask us questions while we're available live, or if not, to email us offline so we can tell you more. So if you'd like to try a codex in this way, log on to the website, which is listed here. The first step is you might have to sign up. You probably don't have an account unless you're a student in my course. If you're a student, then you know what I'm talking about, so you don't need to do that. Step 2, you'll have to enter the course code, and once you do, you'll see the list of available codices. We recommend the one on neural networks. There's also an intro to Julia for data science, but the neural networks one is really fun, and you can see the ways in which we can communicate with you and have a conversation in ways that are different than the run all mode of Jupyter. We love feedback. If you can give us any based on your own explorations of these codices in the demo codex section, please email us at the email address provided, or reach out to us. Google will tell you how.
Thank you so much to JuliaCon for having us, and stay well.